Hello friends, now in this presentation we are going to discuss about the different methods of distillations or the distillation where we can separate the mixtures or the components from the liquid-liquid mixture in the various ways. So there are various ways of distillation process, and from the various ways and the common methods, we are going to focus on the simple or differential distillation. So the contents of this presentation, that is common methods of distillation, simple or differential distillation, and Rayleigh's equation. So from this presentation, students should able to answer the common methods or listing of the methods of distillation, then what exactly the differential distillation is, and derivation of the material balance equation or the Rayleigh's equation. Now basically this distillation is carried out in two ways, that is distillation without reflux and distillation with reflux. So what exactly the reflux is? So I have already discussed in one of the video that the part of the condensed liquid returned to the distillation unit is called reflux. So if you observe this distillation setup, that is plate column, condenser and reboiler. So when we fed the binary mixture or the multi-component mixture in the column, after that, if the feed is in the liquid form, this liquid is going towards the reboiler, and in the reboiler this liquid gets heated, and after reaching the boiling point or changing from liquid to vapors, these vapors are again going back to the column, and these vapors are mixed with the liquid. In the same way, when the majority of vapors are there in the column, so these vapors are going through the condenser, and in the condenser at constant temperature and pressure condition, this vapor is going to convert into liquid with the help of latent removal. So latent heat is removed from these vapors, and without any change in the temperature and pressure condition, vapor phase is going to convert into liquid phase. So these liquid components are collected in the reflux drum, and if the concentration or the purity is not as per the mark or not as per our requirement, then we have to send some of this part of the condensed liquid to the top plate of the plate column, and this liquid component which we are sending from the condensed liquid part towards the top plate, that is called as reflux or liquid reflux, right? So to increase the purity of the product, to increase the concentration of the product, we have to do this activity. So some distillation operation are without reflux, and some distillation operations are carried out with reflux. So the distillation which is carried out with reflux, that method is called as rectification or fractionation. And when we are conducting the distillation processes without reflux, then that may be a simple distillation or that may be a flash distillation. So this simple distillation is also called as differential distillation, and this flash distillation is also called as equilibrium distillation. So let us discuss the simple or differential distillation. So from this diagram, you can understand there is no reflux arrangement in this distillation setup, and that is why it is one of the method where distillation without reflux is carried out, right? So in this diagram, there are different components. The main component is the steel kettle, or it is also called as reactor, but it is generally called as steel or kettle, which is jacketed one. So this is the part that is steel or kettle, and when jacket is provided, that is why it is called as jacketed steel or jacketed kettle. So in the distillation, we have to separate the different components, and that is why we have to provide thermal energy. So in the industries, generally low pressure steam or the medium pressure steam is going to provide, and for that purpose this jacket provision is one of the provision for providing the steam. Sometimes we have to apply coils, half coil arrangement, or some other arrangements. So in general setup, this is the jacketed steel arrangement. So from this jacket, we are providing the thermal energy to the feed, right? So from this nozzle, we are going to provide this feed into the steel. So generally it is a batch process. So whatever the feed you have to feed in that steel, that should be fed only once, and after completion or the separation process, then we have to separate out these residues as well as the final product, and again we have to refeed that particular feed or that liquid mixture. Then there is another nozzle which is for the vapor. So when the thermal energy is provided through this jacket, and when this feed is provided in this steel, so after getting the sensible as well as the latent heat, this feed is going to heat up to the boiling point. If the heat is absorbed by this liquid mixture, then it is called as sensible heat. If after reaching the boiling point temperature, if this liquid is converting into vapors, then that liquid to vapor conversion is taken place with the help of latent heat. So we are continuously supply this steam, and when these liquid components are converted into vapors after reaching the bubble point or the boiling point of pure component, these vapors are going towards the condenser, and in this condenser there is a arrangement that is for the coolant in and coolant out. There is a provision through these nozzles. So this arrows shows as coolant in, and this second arrow outside the condenser shown the coolant out. So coolants are passed through this shell side or the tube side, and these vapors are passed from the other side. So depending on our requirement, again, this condenser is normally shell and tube heat exchanger. That may be a 1-2 or that may be a 2-4 shell and tube heat exchanger. So depending on the properties of these vapors, we are providing these vapors from one side, that may be a tube side or that may be a shell side, and in the vice versa these coolants are provided. So these vapors are converted from vapor phase to liquid phase. That is the main function of this condenser. So condensation means vapors are going to convert into liquid. So these liquid droplets are nothing but the dews in the initial state, and this liquid after some time is called as condensed liquid, and that can be collected in the separate receivers. So this R1 is the first receiver. So for collecting this distillation product or the condensed liquid can be collected in the R1 or the first vessel or drum, and this composition liquid is called as cut. If it is collected in the second collectors or the drum, then it is called as second cut. So likewise, this process can be carried out continuously, right? So this composition of the vapor changes with time. Means initially, if we collect this liquid or the condensed liquid from the condenser into the first cut or the initial receiver, then the composition of the liquid in terms of more volatile component is more as compared to other cuts. So the composition of the vapor changes with respect to time, because if you collect the condensed liquid after some time in second cut, then the composition is again changed, and this change in the composition with respect to time is the mathematical approach, and that is why this distillation is also called as differential distillation, right? So it is a simple process, as we are involving only a steel, we are providing the steam, and after preparing these vapors are going through the condensers. In the condenser, this vapor is going to convert into liquid, and that is why this process is also called as simple distillation, right? So this is one of the simple technique in the distillation. So if you observe the compositions, then we can conclude that in this type of distillation, that is in simple or differential distillation, the product purity is very less, because when we observe, this feed is going to charge only once, and after some time, when this liquid mixture is going to change in the vapor state after reaching the boiling point. So initially, like this, these vapors are generated, and the vapors which are generated initially are nothing but a MVC rich vapors. So more volatile components are the components which are having less boiling point, right? So the initial temperature reaches near to the boiling point of more volatile component, and that is why the maximum vapors which are generated initially are MVC rich vapors. So whatever the vapors which are collected through this condenser in the first receiver are MVC rich condensed liquid. It means in the first receiver, maximum purity or the composition or the concentration is of MVC. So the purest product of this simple distillation is in the first cut, and after that, with respect to time, the second and third cut are having less composition or the less concentration, right? So after some time, if you observe, if most of the more volatile components are vaporized, so obviously at the bottom side maximum LVC is there, and MVC lean environment is created. So at the end of this operation, if you observe, at the end on the bottom side of this steel or kettle, the residual part is of LVC rich. So in the residue, most of the component is LVC, and in the first cut of this process, most of the component is MVC. Right? So if you consider this feed as binary mixture, then A plus B, so A is MVC, B is LVC. So after feeding this binary mixture into the kettle, after providing the thermal energy, and after reaching the bubble point of this mixture, after vaporization of the most of the MVC, this MVC is collected in the first cut. So in this first cut, most of the part is A, that is MVC. And in this residue part, most of the part is of LVC, that is B. So in this way, this A and B can be separated out. That is the main motive of the distillation, that is liquid-liquid component separation with the help of thermal energy, with the help of vapor difference, or with the help of relative volatility. So this is the all about simple distillation technique. Now, if you observe this diagram, from that diagram we can write the feed as a F. So we are assuming the feed in the previous slide is nothing but F. Then the mole fraction of this feed is XF. So it is mole fraction of MVC in liquid phase. Then W is the residue, that is bottom product, and the mole fraction of this W is indicated as XW. So it is mole fraction of MVC in liquid phase, but it is a part of bottom product. And initial one is XF is the part of feed. So F is the feed, XF is the mole fraction of MVC in liquid phase from the feed, W is the residue or bottom product, and XW is the mole fraction of MVC in liquid phase from the bottom product. Then the product indicated as distillate, that is capital D. So distillate is indicated by capital D, and the fraction now in this case is indicated by YD average. So this is the mole fraction of MVC in vapor phase. So that is from the condensed liquid or the final drum, right? So now in this case, if you observe the relationship, then we can write the overall material balance. for the previous diagram. So in the previous diagram, we can observe that the feed is inlet here, feed is inlet, and the outlet is the vapors collected as a liquid and the distillate plus the residue. So the overall material balance at any time during the distillation after vaporization of vapors can be written as L equal to L minus dl plus dd. So L is the liquid, that is in terms of kilomole of the liquid left in the still, and dl is the small element of liquid, and d is the distillate, and small dd is the small element of that distillate which is vaporized or the condensed. So input is equal to output. In the same way, we can write this L equal to L minus dl plus dd. So if you observe this, dl equal to dd, because this L and L will cancel. If you write the individual material balance, for this equation, then we can write L into X equal to L minus dl into X minus dx plus dd into y. So for the individual material balance, we are multiplying with the fractions. So for the liquid fraction, it is x. For the L minus dl fraction, it is x minus dx, and for dd, it is y fraction. Right? So if you observe again, by solving this equation, we can write in the next step Lx equal to L into x. So I am solving this bracket, L into x minus L into dx minus dl into x plus dl dx plus dd into y. So this equation can be simplified in other equation as this Lx and this Lx is going to cancel. So this Lx on the left hand side becomes minus. So Lx minus Lx becomes 0. Now this 0 equal to minus L dx minus dl into x plus dl into dx plus d into dy. Now if you observe, this dl is already small element and this dx is the fraction of that element. So the fraction, if it is multiplied to the small element, the product is negligible, right? So this term can be neglected as the product of the fractions and in the small element is near about 0. Then what exactly remain? So remaining thing is 0 equal to minus L dx minus dl into x plus d into dy, right? So this equation can be written as LDX equal to minus XDL plus YDL, right? So we can take the DL as a common. So equation becomes LDX equal to DL common Y minus X. Now we can rearrange this equation as DL upon L equal to dx upon y minus x. So if we integrate this above equation between the limits, that is when L equal to F, then x equal to xf, and when L equal to W, then x equal to xw. So these are the integration limits what we have applied for this equation. So the equation becomes dl upon L integration limits W to F integration dx upon y minus x integration limits xw to xf. So if you solve this equation, so this 1 by L integration is ln of L, and the limits are W to F. Similarly, this right hand side is dx upon y minus x, but that can be solved like left hand side, so that is remaining same. So our equation becomes ln of f by w equal to integration dx upon y minus x integration limits xw to xf. So this is the final equation for the simple distillation or differential distillation, and this equation is also called as Rayleigh's equation, as this equation is derived by the Rayleigh. That is why this equation is also called as Rayleigh's equation. Now for the material balance purpose, the final equation for this material balance is, that is input is equal to output. It means we can write the material balance of component A over the distillation process is A fed equal to A in still plus A as residue. So for that purpose, we can write the whatever the component A is in the feed, so that can be represented as xf into F. In the still, that can be yd average into D, and in the residue part, that may be a XW into W. So this is the overall material balance equation for the simple distillation, that is XF into F equal to YD average into D plus XW into W. So F is feed, D is distillate, W is waste or residue. XF is the mole fraction of component A in the feed. XW is the mole fraction of component A or MVC in the waste or residue. And YD average is the mole fraction of component A or MVC in the vapor phase as a distillate. So this is the final equation which we can use to calculate the unknown parameters in the simple distillation process. Thank you.